All right, so that's where we're at with predicting our ions. We can look at our electron configuration, look at our highest N values, and know that those can be removed to form ions. And then sometimes a little rearrangement of electron, some lower orbitals, lower subshells can occur to stabilize electron configurations as well. Any questions on any of that? All right. So, let's see where we're at. Okay, very good. Which is a likely charge for the antimony ion? Why don't you guys take 27 seconds to look at this one? What's the likely charge for an antimony ion? And then we'll get back together and, we're not going to break up. We're just going to talk about it in about 20 seconds here. All right, so what do you guys think? Which one of these would be a reasonable charge for the antimony ion? Let's see, who do we got here? Where's my... I've lost my... Oh, there, there it is. Okay. All right. So, Aisha, what'd you get? What's a likely charge for the antimony ion of the ones listed here?
Would it be +3?
That's right, +3. Antimony would lose these 3 electrons first. Another possible charge, Alyssa, that's not here on the list, what might it be?
A -3?
No, well, that's a very good point, but that doesn't, well, I don't know. I'm not exactly sure if that occurs or not. That's a very good point. But as far as positive ions, what would be the next possible positive ion, Alyssa?
+4?
+1, 2, 3, and then you'd have these 2 to lose down here, right?
+5.
+5, that's right. So antimony generally will form a +3 or a +5 in its compounds.
I have a question.
Yeah.
So when you're counting for the 5p, do you count the one it's actually on? Because I had 5p2.
You do.
But I think it's 5p3, right?
That's right, 5p3.
Oh. Okay, thank you.
Mm-hmm. Okay, very good. So, I think we are past this point now. We did have a conversation about this slide here, but we'll review it really quickly. The idea or the fact that this electron configuration game also works for anions, right? Here we have oxygen's electron configuration, helium with 2s2 and a 2p4, and knowing that the p orbital, that p subshell, needs 2 more electrons to be filled. That's another way of thinking about the resulting ion that would form from that atom. All right? It's easier probably for us just to kind of see where it's at on the periodic table and know how many electrons it needs to get to a noble gas as far as our nonmetals go. But it does work with the electron configuration, using the electron configuration as well. All right. Now we're going to turn our attention to molecular compounds. compounds, all right, molecular compounds, and how the bonding between nonmetals in molecular compounds can be kind of understood, and a method which we call drawing Lewis structures can help us significantly understand the properties of chemicals that are molecular in nature. Okay, so Lewis structures. This idea kind of stems from the fact that generally compounds or elements want to have 8 electrons available to them, and that's our octet rule, right? And it works, I mean, the conversation about the octet rule is really most effective when we're talking about molecular compounds, because they're compounds that are made of nonmetals. All right? So I'm going to teach you how to draw these Lewis structures, and as we talk about how we draw them and so forth, we'll begin to recognize their value. Okay? Let's talk initially about the Lewis structure of an atom. The Lewis structure of an atom. The Lewis structure of an atom is just the element itself. So, for example, you write down the elemental symbol for the element, carbon in this case, and then you write dots around it for the number of valence electrons it has. All right? Now, valence electrons for nonmetals, and that's where Lewis structures is really valuable. We'll brush over a couple of examples with ionic compounds, but in general, Lewis structures are for molecular compounds. So, looking at and identifying the number of valence electrons in nonmetals is really easy, right? In our periodic table here, we can see the number of valence electrons simply by the row that the nonmetal is in. So if it's here, it has 8 valence electrons, except for helium. Helium only has 2, right? If the element is in this row or column, 7 valence electrons. Here is 6, here is 5, here is 4, here is 3. We can extend it over here, 2 and 1. Not that we'll be using these, but essentially what we've done is we've numbered these 1, 2, 3, 4, 5, 6, 7, 8 columns, the representative elements, and the number that the element is in, or a number of the column that the element's in, is the number of valence electrons. All right? So carbon has 4 valence electrons, so we make a little symbol like this one here where we put 4 dots around carbon. Now we always want to distribute those dots in a way where we're kind of visualizing 4 regions of electron density around that central atom, or around that atom, whatever that atom is. Okay? Now as we get more than 4, for example, if we're talking about something like chlorine, all right, if I have more than 4, let's see, whose turn is it? Alyssa, can you tell me how many how many valence electrons chlorine has?
7.
That's right. Chlorine has 7 valence electrons, 7th column here, all right? 7 valence electrons, I would draw that like this. 1, 2, 3, 4, and then I could start pairing them up. 5, 6, 7, right? Now, no atom is going to have, well, to start off with, no atom is going to have more than 7 valence electrons. There are some scenarios where we have what's called an expanded octet, and we'll introduce that when the time comes, not far away. But in general, that's how our electrons will be drawn, spread out around the atom. Okay? So why doesn't somebody draw for us an electron configuration for potassium? Okay, so I'm going to stop sharing the board, and I'm going to bring up the multi-user whiteboard here. Anastasia, could you draw for me an electron configuration for potassium on the left? Yeah, on the board there. Are you there, Anastasia?
Yes.
All right.
But I can't draw.
Can't? There we go.
Oh,
There we go.
okay.
Go for it, Anastasia. Potassium. electron configuration. Sorry, did I say electron configuration? I meant the Lewis structure for potassium. Lewis structure for potassium.
sorry.
Potassium. Okay.
Very good. How many valence electrons? What row is potassium in?
Fourth row.
Potassium, it's element 19. Oh, sorry. Not what row, but what column is potassium in?
1.
It's in the first column. And so there's one, very good, one little dot, one valence electron. I think I said potassium. Sorry, I think I said or I meant to say phosphorus. I thought I said phosphorus. But potassium is a good example as well. Brielle, can you draw us the Lewis dot structure for phosphorus?
Yes, I can try.
All right. Camilla, while she's doing that, why don't you draw the Lewis dot structure for selenium?
Okay. What is selenium?
Se, element 34.
Okay.
And if somebody, who's next? Camille, if you could draw the electron configuration for iodine. And if anybody wants to draw their favorite, the electron configuration for their favorite element, go for it. All right, very good. So, potassium, first row, 1 electron. This is our Lewis dot structure for potassium. Phosphorus, not first row, I said first row again, first column. Phosphorus, 5th column, 5 valence electrons like that. Selenium, 6th column, 6 valence electrons just like that. Camille, what are you drawing there? Iodine, there it is. 1, 2, 3, 4, 5, 6, 7 electrons because it's in the 7th column. Okay? Very good. So, the column number that it's in indicates the number of valence electrons, and we distribute the valence electrons as shown here. Okay. Now, you can write Lewis structures for ions as well. Oxygen ion, right? Oxygen atom. How many valence electrons is in an atom of oxygen, Chance? How many valence electrons is in an atom of oxygen?
That's 6.
6. Very good. And if we're going to draw the electron configuration, or sorry, the Lewis dot structure for oxygen, 1, 2, 3, 4, 5, 6. Now, Chance, if I was wanting to draw above it the electron, or sorry, the Lewis dot structure for the oxygen 2- ion, how many electrons would I add there?
More.
That's right, 2 more. 1, 2, 3, 4, 5, 6, 7, 8. All right, so you can do this Lewis dot structure thing for ions. Here's an example here, sodium ion. Sodium ion, no valence electrons, right? Because it loses its electron when it forms a positive ion. So, how many electrons are to be shown on the N3- ion, Chloe? How many electrons should be in the Lewis dot structure for N3-?
Well, normally there'd be 6, right?
Let's see.
5?
5.
Okay, so 8.
That's right, 8. And 1, 2, 3, 4, 5, 6, 7, 8, right? Anytime you kind of take the ion that results in an electron configuration of a noble gas, you should end up having 8 electrons around it, okay? So we can do it with ions, but it's not that big of a deal because the power in the Lewis dot structures is really in the molecule. Okay? Ionic bonds, they form when ions come together, right? When ions come together, and they come together because there's been an electron transfer, right? So the resulting bond is an ionic bond, a bond between oppositely charged ions. And we talked about this lattice structure, which becomes so strong because all of our elements, all of our ions have many neighbors. See this positively charged sodium atom, or ion here, that my pointer is pointing to, Daisy. Can you count, and you'll have to think three-dimensionally here, if this was in the middle here, how many neighboring chlorine ions does that sodium ion have, Daisy?
So the sodium is the little circle in the middle?
It's the little silvery one, right? The chlorines are the green ones.
So you're asking how many chlorines?
How many chlorine neighbors does this sodium, would it have if it was right here in the middle?
Well, it has 4 around it. Like square it. It's gonna be like
It has
60.
it has 4, and I'm talking about the neighbors right around it. It has one above, one below, one to the right, and one to the left. But there's another one that we can't see, isn't there?
Oh yeah.
Back behind there. And there would be another one in front if we weren't cutting it in half right here. Can you see that?
Okay.
So it would have
So
how many neighbors?
there'd be 6.
6
around it?
neighbors. That's right. And if you think about this chloride ion right here, the green one, Daisy, how many sodium neighbors would it have if it was in the middle of a three-dimensional lattice like that?
That would have 4.
1, 2, 3, 4, as it's drawn here. But if it was in the middle, how many would it have?
If it was in the middle, it would have 1, 2, 3, 4, 5, 6. It would have 6 as well.
And that's right. That's right. So that's another indication or another explanation for why these lattice structures have kind of so much energy inside of them, right? How much they are stabilizing these ions significantly, and it requires a lot of energy to break them apart, right? They're not high energy, they're stable. They release a lot of energy when they form. Okay? So that's our ionic compounds. A Lewis dot structure for an ionic compound is really boring. For potassium sulfide, for example, it's the Lewis dot structure for the sulfide ion and the Lewis dot structure for the 2 potassium ions. And this doesn't tell us anything really helpful. Again, Lewis dot structures are not extremely helpful for ionic compounds. They're helpful for molecular compounds. So let's get into how they help us describe molecular compounds. In a molecular compound, or a molecular bond, a bond where 2 nonmetals come together, what's happening is, just like these 2 hydrogen ion or atoms here, you could represent these 2 hydrogen atoms as their electron cloud around them as spheres, because it is a 1s orbital, which is occupied by an electron in hydrogen. And as you bring those 2 spheres of electron density close together, neighboring electrons will be attracted to neighboring protons, and the result will be a sharing region of electron density. Okay? This is symbolized as follows in terms of using our Lewis dot structures. Hydrogen, there's the Lewis dot structure for hydrogen, right? Everybody comfortable with that, hopefully. Here's the Lewis dot structure for hydrogen, 2 hydrogens. We bring them close together, and we can show those dots like that, all right? So 2 hydrogens coming together, sharing 2 electrons, one from each hydrogen atom, right? Another way to express that is to draw it like this, where we've replaced those 2 electrons that are keeping those hydrogens together. We express it as a single bond, like that. So whenever we see that kind of a bond, for example, if we see something like this, what that means is the sharing of 2 electrons, one from this carbon and one from that carbon. Okay, so Emily, how many electrons does that bond represent?
2.
2, that's right, 2 electrons. 1 electron from this carbon and 1 electron from that carbon. Okay? The other way that we could kind of draw, for example, an oxygen, well, we won't get into that yet. Okay, very good. Now, let's look at this. Well, let's see. I thought I didn't want to share that. Yeah, I don't want to get into that right now. If we look at the energy, the collective energy of 2 atoms of, let's say, hydrogen, right, versus the distance that they're separated from each other, we would form a plot something like this. All right? Initially, 2 atoms of hydrogen that are far apart from each other have relatively high energy because there's room for more electron density around that hydrogen atom, right? We know that there's a change in energy when an element gains an electron. And let's see if you can remember. Falata, do you remember what happens when, in terms of energy, when you give an element an electron? If I give an electron to any one of these elements, does it stabilize the element, release energy, or does it increase the amount of energy, or does it just depend on what element gets the electron? Do you remember, Anastasia? Or let's see, who was it? Falata. Do you remember?
It depends.
Okay, it actually, for every single element that I give an electron to, it will always release energy. Always release energy. And what do we call that? What's that process, Joey? Do you remember what that's called? This process where we take an element, give an electron, and make a charged element, right? Is this ionization energy or is this electron affinity, Joey?
Is that electron affinity?
That's right. Electron affinity. Electron affinity. And always, the first electron, right? The first electron will always have a change in energy of a negative number, right? Everybody will always take 1 electron. For this reason, when you have a single nonmetal by itself atom, single atom of a nonmetal, 2 of them, or any number of them, all by themselves, their energy is relatively high and can be stabilized by approximating 1 atom to another atom. Now, if you get those 2 atoms too close, then they begin to repel each other. The electron density and the nucleus, both of them will work against each other if they're too close and begin to repel. And that will increase the energy. But there will be a sweet spot here where we've maximized our energy. And that distance represents the bond distance between 2 atoms. So initially, their collective energy is high, but as you bring those 2 elements close together, they share electron density, stabilize each other. If you get too close, the energy goes back up again, but this distance here represents the bond distance between 2 elements. All right? And hopefully you can remember this as well, because this is usually a question that's on some test if we haven't had it already. Here's element X combining with element Y to form compound XY. Delta H for this reaction, is it positive or negative? Kylie, positive or negative for this reaction? Or can we not tell? Or does it depend?
information, but I'm not sure.
Okay. Well, if it's an element, if these are elements, and they've formed a bond, then that process will always release energy, right? The sheer fact that a bond is formed means that the process releases energy. It doesn't matter if you're forming a bond, you're always releasing energy. Same as the ionization energy, right? Taking an atom A, giving it an electron, that will always release energy. All right, the first electron. The second electron, not necessarily, but the first electron will always release energy. Same with this question here. Anytime a bond is formed, that releases energy. Element X and Z are in a compound. That bond is broken, and element X and Z are in compound XZ. That bond is broken and forms element X and Z. The delta H for this process, Rebecca, has to be what? Negative or positive?
Positive?
It has to be positive, because I am doing what? How did we know it has to be positive?
Because you're not releasing energy.
Yep, but how did I know I'm not releasing energy?
Because you're breaking a bond.
That's right. Anytime a bond is broken. It's a fundamental fact of the universe. The existence of absolutely anything, right? You break a bond, energy has to go in. You form a bond, energy comes out. All right? Cannot be denied no matter where you are in any existence throughout any time or eternity. Okay, so bond energy is based on the maximum or the ideal distance, and how much energy of stabilization is kind of governs that distance. If the distance is very large here, then the bond isn't very stable. It doesn't stabilize the atoms very much and can easily be broken later on. Still requires energy, but not as much. The energy required to break a bond then is called the bond dissociation energy. Okay? Hopefully that's not terribly surprising. It's the energy required to break a bond dissociation energy. All right. So, when we bring nonmetals together to form molecules, they want to follow this octet rule in general. Some exceptions are hydrogen and helium, right? Hydrogen doesn't want to have 8 electrons around it. Can you tell, let's see, whose turn is it? Sarah. How many electrons does hydrogen want to have around it? Not 8, but how many, Sarah?
Does it want to have 2?
That's right. It wants to be like helium. It wants to have 2. So in that case, it's kind of like the only exception. You could think of helium as an exception as well. These 2 atoms are wanting to have an electron configuration similar to that of helium. All of these obviously want to be like neon, right, moving down. So they all want to have 8 valence electrons around them. Chlorine, if I draw the Lewis dot structure of chlorine up to the top, who's up at the top there? Aisha. If I draw the Lewis dot structure of chlorine here, okay, atom of chlorine, how many electrons around an atom of chlorine in a Lewis dot structure? 7. That's right. It's in the 7th column here. All right. 1, 2, 3, 4, 5, 6, 7. Right. Here's a little bit tougher question, Aisha. How many electrons does an atom of chlorine have? What's that? How many electrons, does an atom of chlorine have? Oh, Aisha lost connection. Alyssa, do you recognize how many atoms an atom of chlorine has? Sorry, how many electrons an atom of chlorine has, Alyssa?
Electrons or valence electrons?
See, and that's the point, right? We want to make sure we recognize that when we draw 7 electrons around chlorine, or if we're talking about sulfur, if we draw 6 electrons around sulfur, we're not drawing the total number of electrons, right? It's the number of valence electrons, okay? So chlorine has 17 electrons, but we only draw 7 around chlorine atom when we're drawing the Lewis dot structure. Okay, so molecules follow this octet rule and try to fill their outer shell with 8 electrons and have 8 valence electrons around them. When they do this, when they form bonds, when 2 atoms form bonds, so here's chlorine, and I'm going to draw a hydrogen, right? We can see that chlorine wants to kind of fill that space there, and hydrogen wants to fill that space there. And so we can, kind of like Legos, match them up and draw ourselves a compound like that, where again, this bond, how many electrons are represented by that bond, Anastasia? Anastasia, are you there? How many electrons are represented by that bond?
1.
No. Okay. We are drawing, this represents 2 electrons. It represents that electron from chlorine and that electron from hydrogen coming together. So in every bond, it represents 2 electrons. Now, those are just 2 valence electrons, right? So if I draw something like this, H2O, water, right? How many valence electrons are in the bonds there? Who is it, Brielle? How many valence electrons are in the bonds of this molecule of water that I've drawn?
In the box, there's 2 in each, so there's 4 total.
That's right. So there's 4 electrons in these bonds. And if I include what are called the non-bonding electrons, these ones here, there's a total of 1, 2, 3, 4 in the bonding and 5, 6, 7, 8 in the all together. So there's 4 electrons that are bonding, and we also have in the water molecule 4 electrons that are non-bonding. Okay, so in a molecule here, how many bonding electrons and how many non-bonding? How many bonding and how many non-bonding? Okay, let's see. Is it Camille's turn? Did I skip Camilla? Whose turn is it?
I don't know, but I can go.
All right, go for it, Camilla.
Wait, will you repeat the question?
Yep. In this molecule here, how many bonding electrons and how many non-bonding electrons?
You have 2 bonding.
Mm-hmm.
And then 6 non-bonding.
1, 2, 3, 4, 5, 6. Excellent. Okay, so Ephraim had a question. Why are we not including D block when we're talking about Lewis dot structures? All right, why are we including the D block elements? Well, the Lewis structures are, again, something that we've invented, right? It's our own model to help us visualize compounds, all right? And it's only really effective for our nonmetals, okay? In any ionic compound, you'll rarely ever, and if you do, it's really not an effective conversation to talk about ionic compounds with Lewis dot structures. This is really majorly helpful for our molecular compounds. So that's why we skipped those D block elements when we were identifying the number of valency electrons. And I counted across using these elements just to help us recognize that we are counting columns 1, 2, 3, 4, 5, 6, 7, 8 to help us know how many valency electrons, right? So we could just count from here 8, 7, 6, 5, 4, 3. That would be fine because really it's only going to be about these elements, these nonmetals, where this is critical, but either way. All right, looks like we're out of time. So we'll talk about unequally sharing electrons next time. If you have any questions you want to hang around, that would be fine. If you didn't get to go to my Tuesday lab section yesterday, the video of what we did is on the homepage of that of the Canvas page, and you definitely want to go check it out. You definitely want to be starting on those exercises. Make sure you can get those done for yourself so that you can collect all the points. It should be pretty straightforward. If you do the exercise, you're going to get the point. Now, it's not easy to do the exercises in some cases, but if you watch that video, we essentially do 2 of them together there, or at least show you how to do 2 of them, and that should be pretty straightforward. For those of you who have questions about the latter ones, please send me the questions. I think the best way to send me the questions is through my email address. I don't really have a good way of being reminded on Canvas of questions that I have, so I think the best way is through my email address. If you have any other questions you want to hang around, I'll be free to answer them. All right. Yes.
So when is exactly the final exam?
It'll be the 15th. It's going to be a multiple choice exam online, just like our quizzes, our practice quizzes. It'll open the 15th. It'll probably, yep, on Canvas. It'll be open the 15th. It'll probably last for 3 days, maybe 4 or 5.
Does it have a time limit?
I'm not sure yet. I mean, definitely it's going to have some time limit, but I'm not sure if they're going to govern the time limit. So typically, I say there's a 2-hour time limit. We take the final, and nobody's there for more than an hour and a half. That's how it usually works every year. But this is new territory, so I'm not sure. There will be some time limit, but generally time limits aren't the thing that rushes people through the problems. This last exam, I put a time limit on it because I wanted you to take it to know where your knowledge was right initially, not the last exam, but the last practice exam. I want you to take it once to test your knowledge, to see where you're at. And then after you've done that, I don't mind if you guys take longer on it. In fact, I should probably extend the time so you guys can look at that longer. But I've increased the number of times you can take it as well. So
Can we take again the practice?
yeah,
exam?
yeah.
Okay.
How many times have you taken it, Ephraim?
I haven't. That's what I'm asking for.
Okay.
And then will the final exam just, is it through Canvas alone, or are we using Proctorio within Canvas?
Yeah, we'll be using Proctorio.
Within Canvas, okay. Thank you so much.
Yep. Any other questions?
What were you saying that we could do on Canvas for points? Were you saying something like that?
Nothing for points.
Okay.
What was I
That's
saying? Yeah, I think I was just saying, I don't know. Oh, for the lab, yeah. So if you're in my section for lab, you'll want to make sure you can do all of those 7. Depends on your section, right? So if you didn't get to do lab 5, then you have 7 of those write-ups that you want to try to accomplish. If you got to do lab 5, then you only have to do 5 of those exercises. Each of them are worth 10 points. So you just want to make sure you get through those and collect as much points as possible. All right, any other questions? Okay, see you guys later.